Okay, so yeah, let me. I'll just talk briefly about the midterm. Okay. Okay, so it'll be about 35 to 40 multiple choice. Questions, okay. You'll have 1 hour, 45 minutes for the exam. Okay. Yeah, make sure you bring everything listed there, but especially, bring your reference tables. And make sure your calculators work, okay? Okay, and then and you are allowed a allowed one note sheet with writing on one side. Okay, and I'll provide the Scantrons. Okay, we will have there will be lecture on after the test, but I'll cover how to do the lab assignment. Okay, so so after the test. So you will have a lab assignment where you are exploring confidence intervals, okay? And that will be due the week after the midterm exam, okay? So so next week will be the midterm, and then after that you'll have this lab assignment due, okay? And so after the test we'll have that, okay? As far as today goes, we will wrap up Chapter 6. Okay, Chapter 6 in confidence intervals. And then I will introduce Chapter 7, okay? But Chapter 7 is not covered on the midterm exam, okay? Okay, and then after introducing Chapter 7, we'll just kind of do a very, very brief review for the midterm. Yes?
So we're allowed one note sheet and we're allowed 3 note cards?
Okay, so okay. So one note sheet. So you have the choice, because some students said I prefer to use note cards rather than a sheet of paper. Okay, so you have one choice. Okay, you can have 8.5 by 11 or 3 by 5 note cards.
One side is
The note cards are double-sided. Okay. The 8.5 by 11 is single-sided. Okay. I think most students opt for this, but every now and then a student will say, "Can I use note cards instead?" And so the answer is yes. 3 by 5s. Okay. And they both give you, you know, what is 8.5 times 11? I don't know what 187 divided by 2 is. 93.5. Okay, 3 by 5 times 3 front and back would be 90 square inches of real estate that you can write on. Okay, so they're about the same. Okay. Okay, so we good here? Okay, so we'll keep talking about confidence intervals. Okay. Okay, so so far, or I'll say last week, we created a confidence interval for the population mean mu based on the sample mean y bar. Okay, or in short, we would just call it confidence interval for mu. Okay. Otherwise, you know, but this, you know, when you say I'm making a confidence interval for mu, that means it's always, the confidence interval is always for something about the population based on the equivalent version from a sample, right? So we could, you know, we're not going to cover how to do this, but we could make a confidence interval for sigma, right? And that would be based on what? The sample standard deviation S, right? Okay, but that comes with a different set of rules, so we're not gonna do that. Okay, and the big idea for confidence intervals is that you know, we do not know the value of mu, which is our, you know, population parameter. Okay, and the population is too big to observe directly. You know. Okay, but you know, so we take a random sample. Okay, and based on our sample mean, okay, y bar, we create an interval of plausible values of mu. And then, you know, the width of our interval is based on the variation or the spread that exists within the sample. All right, and so our our formula for a confidence interval is centered at y bar. Okay, so the I guess formula is y bar plus or minus t star times s over the square root of n. Okay, so s over the square root of n, this is known as the standard error. Okay, or we can also think of it as our estimate of the standard deviation of the sampling distribution. Okay. So the sampling distribution is, that the normal distribution that describes where different y bars, or the values of the different sample means y bars could be. Okay, and so this s over the square root of n, it's our estimate of this value. Okay, because the true value is what? The true value of the standard deviation of the sampling distribution is sigma over the square root of n, right? You guys just took a quiz on this? Okay, I mean, maybe I'll... True value of, the standard deviation of the sampling distribution but this requires that we know what sigma is, which we don't. So we use S as our best guess. Okay, all right. T star, this is called our critical value. And, this is kind of we would normally use the normal distribution because we know that y bar, the sampling distribution of y bar, is normally distributed. But the t distribution takes into account the uncertainty that exists in our standard deviation estimate. And so, so the t distribution is just is like a wider version of the normal distribution. Okay. Okay, and then y bar, this is our sample mean, and serves as the center, serves as our best guess, current best guess. Of mu, and is the center of our interval. Okay, and this quantity, so in y bar plus or minus t star times s over the square root of n, this quantity, this is known as our margin of error. Okay, so essentially we've got y bar plus or minus the margin of error. And this thing works, the confidence interval works, because from our understanding of the central limit theorem, we know that y bar follows a normal distribution. Okay? Tells us that any y bar we see comes from a normal distribution centered at the population mean mu. Okay, as long as our conditions are met. Do you guys remember what those conditions were for the central limit theorem to apply?
Sample size?
Okay. Yeah, okay, so these are all kind of true, but so the conditions are your sample has to be randomly selected, okay, so that's a very important one that we can't ignore, okay? Your sample has to be randomly selected, and each thing in your sample has to be independent of each other, right? So you can't just randomly say, I'm going to take these people. So everyone needs to be independent, so they need to be randomly and independently selected, okay? And then, yes, your sample size needs to be big enough, which we said in most cases 25 or more is big enough. If the population we know is normal, then small samples are okay, but if the population is really skewed, you would need even bigger samples. But rule of thumb, 25 or more, big enough in most cases. There's also a flip side, and this is related to the fact that the sample needs to be selected randomly and independently, is that you can't sample too much of the population. This is rarely a problem because generally our populations are huge, but if you're dealing with a small population, say you're taking samples from a select group of people or something, you don't want to sample too many people because at that point the people you select stop being independent of each other. So just to explain, let's say, the first time you take a card out of a randomly shuffled deck, the first card has a 50% chance of being red or black because there's 26 red and 26 black cards, okay? But technically, after you draw out that first card, let's say it's red, the next card no longer actually has a 50% chance of being red or black. It's 25 red is left in the deck and 26 black are left in the deck, okay? And so, maybe after drawing one card, the difference that it makes is fairly insignificant, okay? And so a lot of times we just say we ignore it. But, once you start drawing over 10% of the deck or 10% of the population, after you've selected 5 or 6 cards, what remains in the deck can actually be dramatically affected by the cards that you've drawn. So that's rarely a problem that we encounter, that drawing a sample size that's too big, but it could be an issue at some point. So most of the time, the problem that you deal with is you didn't get a big enough sample, but occasionally you can have problems where you're sampling too much. And then it just becomes, well, maybe you should just sample the entire population and do a study on the entire population if you can get a hold of everyone that way. Okay, so this is what we've covered. So this is okay. We did this, all right. Okay, so now we can extend the confidence interval to make inferences about two populations. Okay, and basically, you have population 1, and again, it's too big. Population 1 has mean mu1, okay, and then you've got population 2. Okay, and this has mean mu2, okay? And from population 1, we've taken a little sample, sample 1. And from population 2, we've taken a piece, and this is sample 2. Okay? So sample 1 will have mean y bar 1, standard deviation S1, and size N1. Okay? Sample 2 will have y bar 2, S2, and N2. So the samples don't even have to be the same size, and that's fine. Okay? The question is let's say y bar 1 and y bar 2 are different, okay? And that's almost always going to be the case, right? If y bar 1 and y bar 2 are different, does that mean that that mu1 and mu2 are different? Okay, this is the question that we have, right? So what we're going to do is we are going to create a confidence interval, not for mu1 and not for mu2 individually, but in order to answer this question, we're going to create a confidence interval for the quantity mu1 minus mu2, the difference, okay? So so we're going to create an interval of plausible values that mu1 minus mu2 could be. Okay, so plausible values of the difference. Okay, so just to check our understanding here, let's say the example is population 1 is adult males, and population 2 will be adult females. Okay, and we'll just say in the US. Okay. All right, and so the question is, we take a random sample of adult males, we get their average height, y bar 1. We take a random sample of adult females, and we get their average height, y bar 2. Okay, and based on y bar 1, the average height of our sample of men, and our y bar 2, our random sample of women, we are going to create an interval of plausible values for mu1 minus mu2. Okay? So what do you think our interval will look like? What kind of numbers do you think we'll get? am I going to get numbers on the order of 5 inches, or on numbers on the order of 5.5 feet, or numbers on the order of something much bigger or much smaller? What do we?
Wouldn't it be like an extremely big number? If you're doing the population of adult males in the United States?
Yeah, so we're talking about mu1 minus
okay.
mu2, okay? So what is mu1? What is mu1? Well, like what's a plausible, okay, if I created an interval, okay, I'm sorry. So example, population is adult males, population 2 is adult females, and you know, that we are measuring their height. I'm sorry, maybe I skipped saying this, I don't know. So we're measuring their heights, okay, so y bar 1 would be the average height of the random sample of men. And y bar 2 would be the average height of the random sample of women. Okay. And what we're doing is we're creating an interval for mu1 minus mu2. Okay, so what is mu1? What does mu1 represent? This is the the population mean height of all men in the US, of all adult men. And mu2 would be the population mean height of all adult females in the US. So what would plausible values be? Like, what's a plausible confidence interval for the quantity mu1 minus mu2?
So like 3 inches?
Okay, yeah, so I would say anywhere from 3 to 7 inches, 3 to 9 inches, okay? You know, we're basically asking the question, what is the height difference between the average male and the average female in the United States? Okay, what's the height difference between the average male and the average female? And we would say, you know, the height difference, or the average height difference between the average male and average female is somewhere between, I don't know, 4, 5, 6, 7, 8, 7 inches, something like that, okay? Probably around 5 to 6 inches, something around there. And depending on the data we've collected, you know, maybe we need a large interval or a small interval, okay? Does that make sense? So we're not talking about, you know, the average height of an adult male might be 5'10" or something like that. And the average height of an adult female might be 5'4" or 5'5" or something like that. And if that's the case, then we have a height difference between the averages of, you know, 5 to 6 inches. Okay, so our answer is not going to be 70 inches or 5'10", and our answer is not going to be 64 inches, but it's the difference. Okay? So, you know, a possible confidence interval for mu1 minus mu2 would be, you know, 4 inches to maybe 8 inches. Okay, I'm just making stuff up, but something like that. Okay. All right. What if instead of measuring their heights, we measured IQ scores? Okay, so let's say we were measuring people's IQs, and so population 1 is men, population 2 are women, and we want to know what's a plausible range for the difference between the average male IQ and the average female IQ.
Negative.
Okay? Huh? So just make up a number. But what do you think? What do you think a plausible range would be?
1 to 3.
Okay, so you said negative.
Yeah.
Okay, so negative what to what?
I mean, it could be maybe like -20. Is that
For on the low end, and on the high end we would have
+20?
positive 20. Okay, yeah. So this brings up a very good point. Okay, so for when we're talking about height, I don't think anyone's going to dispute the fact that on average men are taller than women. Okay, but as far as intelligence or IQ scores, whatever it tries to measure in the United States, probably on average about the same. Okay, and so when we create the interval for IQs, what we're going to have is going from the negative side to a positive side. Okay, so maybe -20 to positive 20 would be a huge range, but I would definitely say from negative something to positive something, meaning that when we're talking about what is the difference between the IQ of the average male and the IQ of the average female, that difference could be anywhere from where the average male is anywhere from 10 points lower to 10 points higher than the average female, okay? With probably 0 being the most likely difference, okay? So in that case, 0 is within the range of plausible values, and we would then conclude our data does not provide evidence that there's necessarily a difference between average IQs. Whereas in our case, when we're talking about heights, the difference is entirely positive, from 4 inches to 8 inches, meaning the average male might be anywhere from 4 inches to 8 inches taller than the average female, giving us evidence that males on average are taller than females. Okay. Does that kind of make sense what I'm saying? Okay, so I'll write that on the next slide. Okay, so example 2. So population 1 will still be male, and population 2 female. Okay, but this time we are measuring IQ. Okay, so plausible range of values for mu1 minus mu2 probably can be something like -10 to +10. Okay, and so the interpretation would be we are whatever confident that the average IQ of males is anywhere between 10 points lower and 10 points higher than the average IQ of females. Okay, so what we have here is that 0 is a plausible value for the difference between average IQs. Okay, so in this case, so we would not have evidence that there is a difference between average IQs. Okay, so we are creating intervals for the difference, and so if that interval contains 0, we would not have evidence that there's a difference between the mu's and the population. There could be a difference, but until we actually find out the true value of mu1 and mu2, we have to just say, you know, we haven't taken a big enough sample to answer this question yet. Okay. Okay. Whereas, you know, versus the height example, okay, you know, for heights, you know, our interval was from plus 4 inches to plus 8 inches, right? Okay. And so in that case, you know, our entire interval is entirely positive, okay? So the entire interval is positive. Okay. 0 is not within the range of plausible values. Okay. So in this case, we would have evidence. We do have evidence that the average height of males is greater than the average height of females. Okay. Are we feeling okay with the interpretations here? Okay, so then I'll show you the formula for calculating this, which is, I think, fine. Just a tiny bit more complex. Okay. So, all right. So just I'm going to just say recall for mu, the confidence interval is y bar plus or minus t star times s over the square root of n. Okay? So now the confidence interval for the quantity mu1 minus mu2 is, okay, over here it's going to be y bar 1 minus y bar 2 plus or minus t star times the square root s1 squared over n1 plus s2 squared over n2, okay? And so, you know, if we look at this, we see that it kind of follows a similar form. Here's our critical value. Okay. This quantity, it's still called our standard error. Yes?
Why is the whole thing square rooted?
Why is the whole thing square rooted?
It's just the end.
S over the square root of n. Yeah, I'll illustrate, kind of explain this in a moment here, okay? And then this is our current best estimate of mu1 minus mu2. Okay? So yeah, what is this? Why is this thing like this? Okay? Well, we didn't cover this, but when you combine random variables, okay, the variance of the combined random variable is the sum of the variances, okay, which is different from just simply adding standard deviations, okay? So standard deviations are the square root of the variance, okay? So what ends up happening is you end up getting a picture like this. Okay, so on this side we can have, let's say, s over the square root of n, and we will label this side 1. So s1 over the square root of n1. And over here you have s over the square root of n2, okay? Or s2 over the square root of n2. Okay, what is this side over here? Okay, so we would have, you know, a squared plus b squared equals c squared, right? So I would do s1 over the square root of n1 squared. Basically, this is to get the variance. I'm squaring. To get the this thing, I'm adding up the variances, not the standard deviations. And that's, you know, we didn't cover this, but this is basically this side right here, c squared. Okay, so I end up getting, this one ends up being s1 squared over n1 plus s2 squared over n2, right? And this is c squared. So if I want to get c, I would just take the square root of this side. And that's how we're getting this. Okay? It's not too bad. You just have this. Okay. All right. Let's do one of these examples, and then we'll take a short break here. Okay. All right. So. Okay, so I will say, you know, do, I don't know, is the, I don't know, average weight of a house cat more, or I'll say different, from the average weight of a, let's do a Yorkshire Terrier. All right, what do you think? I don't know. I've got to go on Google here and ask this question. What's the average weight of a house cat? We can just make up numbers too. 7.9 to 9.9. So we'll say sample 1 will be the cats. Okay, we got y bar 1, s1, and n1. So I'm going to just make up numbers. We'll say 8.9 pounds. And there's some fat cats too, right? So we'll say the standard deviation, I don't know, 1.6 pounds, and we'll say we took a sample of 12 cats. Okay? All right. Average weight of Yorkie. Is that the same thing? But can weigh as much as 12. Show dogs should weigh between 4 to 7, but pets can weigh between 12 and 15. Well, that's troublesome. Show dogs should be between 4 and 7. Okay, so we'll say sample 2 will be the Yorkies. I don't know. This is... Yeah, and I know some cats are like 15 pounds also, so... okay, well, we're just going to make up numbers because I can't. We'll say 7.6 pounds, and the standard deviation will be 2.4 with, and we'll take a sample of 10. Okay, so now it's just a matter of plugging and chugging. Oh, I've forgotten an important thing, and that is, how do we pick our T star? Okay. So T star is based on our degrees of freedom. We need the degrees of freedom. So df for T star. Okay. So there is a formula for getting T star, and it's quite complicated. And even that formula is actually an approximation, because when we are dealing with samples that have different standard deviations, things get complicated. And so we have two, so there's a formula to approximate the degrees of freedom, but because that formula is still complicated, we have another way to just approximate that formula. Okay? And so there are, we can approximate this. Okay, so we'll approximate degrees of freedom with n1 plus n2 minus 2. Okay? Now, if you read another textbook, it might say approximate degrees of freedom as n minus 1 and use the smaller of the n's. Okay? So I'll put that over here, and I'll say other texts may say degrees of freedom is equal to n minus 1 and use the smaller of the two n's. Okay? And so the truth is that the degrees of freedom is almost always going to be somewhere between these two numbers. Okay? Just so everybody gets the same answer and whatnot, we'll use this one in class. We'll use n1 plus n2 minus 2 degrees of freedom. Okay? You know, if you have a computer, it will do the more complicated approximation formula, which is pretty good, and so you don't have to worry about it. But you know, if you're going to look up values in the table yourself, we will use n1 plus n2 minus 2. Okay, so go ahead and take a couple minutes and create a confidence interval for the difference between the average weight of a cat and average weight of a Yorkshire Terrier. I'm going to pause the video here. Let's go over this. Alright. Okay, so just plugging in the current observed difference, 8.9 minus 7.6. And it's totally, well, I'll talk about what happens if we had labeled our samples opposite, okay? 8.9 minus 7.6 plus or minus T star. So when I count my degrees of freedom, I've got n1 plus n2 minus 2, and I get 20 degrees of freedom, right? So I look up 20 degrees of freedom, 95% confidence, and I'm getting 2.086. So T star, 95% confidence, degrees of freedom 20, I got 2.086 times, and I'm just going to plug in 1.6 squared over 12 plus 2.4 squared over 10. So punching this into the calculator, 1.6 squared divided by 12 plus 2.4 squared over 10. Okay. So I like to just punch this in and then take the square root of the answer, and I get 0.888. Okay, so I got 2.086 times 0.8884. So I'm going to just multiply this by 2.086. All right, and I get plus or minus 1.853 as my margin of error. Okay. 8.9 on the other hand, 8.9 minus 7.6 is 1.3. So I have 1.3 plus or minus 1.853. Okay? All right, and so if I do these things, okay, 1.3 minus 1.853 gives me negative 0.553, and on the other end, I get 3.153. Is that okay? All right, so let's, I'm going to take this to the, our results here. And so this is my resulting confidence interval. And I would say, you know, so keep in mind, you know, sample 1 were the cats, sample 2 were the Yorkshire Terriers. Okay. Are any pro sports teams called the Cats? Just like the Bobcats, huh? All right. Anyway. All right, so I would say something like, I am 95% confident that the average weight of cats is anywhere between basically 0.553 pounds less and 3.153 pounds more than the average weight of terriers. I don't know who this is. I should turn off these notifications. Okay, so to answer our original question, do we have evidence that the average weight of cats and the average weight of terriers are different? Yes? No? So let's go back. Do we have evidence that the average weight of cats and the average weight of Yorkshire Terriers are different? Oops.
Yeah.
So the answer is no. Okay, and the answer is no because 0 is a plausible value in our interval. Okay, 0 is a plausible value.
But it's 0.5.
It's negative 0.5. Yeah, so it's because it can be anywhere from 0.553 pounds less to 3.153 pounds more. So 0 is a plausible value for the difference between average weights. Is that okay? All right. Now, what would happen if I used a different confidence level? Okay, so let me just flip back a slide. Okay, so I'm going to come to copy just basically this. Okay, so I have this, but let's say, what if this was the work that we had before? What if I used not 95%, but what if I used 60%, created a 60% confidence interval? What would I end up having? So let's say make a 60% confidence interval. Now, people rarely make 60% confidence intervals, but let's say we did make a 60% confidence interval. Everything else stays exactly the same, right? This is still 8.9 minus 7.6. This is still this. The standard error is still this. The only thing that changes is I'm no longer using 2.086. I'm using 0.860 as my T star. Can you guys see that? So I'm no longer using 2.086. I'm using 0.860. So the only thing that changes is now I have a smaller t. Okay. So making a 60% confidence interval, the only thing that changes is now I use a smaller t. Okay, so so let's just do the math, and we'll calculate what happens. Here I get 1.3 plus or minus 0.860 times 0.884, or 8884, and I get 1.3 plus or minus 0.764. Okay, so 1.3 minus 0.764, that takes me from 0.536 to, oops, 1.3 plus 0.764, 2.064.
How'd you get 764? I got 760.
760. Did I type something wrong? 0.860 times 0.8884. That's what I'm getting. Okay. All right. Is this part okay? Everything here? So what happens now? So now I would say I'm 95% confident. Or I'm sorry, not 95. Blah blah blah. Bad. Okay, I am 60% confident that the average weight of cats is between 0.536 pounds more, or 0.536 pounds and 2.064 pounds more. Than the average weight of terriers. Okay? So in this case, would we say, do we have evidence that the average weight of cats and the average weight of terriers are different?
Yes.
We would say yes. We have evidence that cats weigh more than terriers, okay? Now, so we would say yes, we have evidence that the weights are different, that the average weights are different. Okay, actually, and we have, we have evidence that cats weigh more, okay? All right, we use the exact same data, right? So how can over here we're making a decision, no, we don't have evidence that there's a difference between the average weights. We don't have evidence that there's a difference between the average weights. And over here, we're using the exact same data, and now we're saying, yes, we do have evidence that the average weights are different. Average weights are different. Cats weigh more. How is that possible? Yeah, we changed our confidence level, okay? So here, if I'm willing to be less confident about my conclusions, I can start saying things like, I feel like cats weigh more than dogs. Or not I feel like, I can say, I have evidence that cats weigh more than dogs. But then somebody says, well, how confident are you in your decision based on the evidence you have? You have to say, I'm less confident about this. And then on the other hand, if you want to be more confident about the statements you're making, that might lead you to be, quote, more cautious in saying, like, yeah, in our samples, the cats weighed more than the dogs, but it wasn't such a dramatic difference that I can't rule out the possibility that zero is a plausible value. So, when you're trying to be more confident, you're less likely to come to a conclusion that there actually is a difference, if that makes sense. Okay, so lower confidence gives you a smaller interval. If you want to be more confident, you have to take a wider interval, and the wider interval might mean you are making less exciting conclusions. Okay. On the other hand, notice I'm saying, do we have evidence that the average weights are different? Okay. If the question here is, do we have evidence that the average weights are the same? What is the answer there going to be? No. The answer is always going to be no. Okay? We will never have evidence that the average weights are the same. Okay? Because if we actually go back, the average weights of our two samples were different. Okay? So remember, our question is, do our samples point back to the populations and say the population means are different? Okay? We cannot say just because I don't have evidence of a difference means I have evidence that they're the same. Okay, so that's worth writing on another slide. So you're not having evidence of a difference is not the same as having evidence that the means are equal. Cool. And statistics is just not the way we approach these problems. They're just not set up to be able to answer the question, are they equal? Okay. Are two population means equal? Okay. We can only answer yes, they're different, and I'm not sure if they're different. Those are the only two answers we can come to in statistics. I have evidence that they're different, and I'm not sure if they're different. Okay, well, actually, it's always, I'm not sure if they're different, but just, I have evidence that they're different, and I don't have enough evidence to say that they're different. Okay, so we only two conclusions are allowed. Okay? You cannot say this means the means are the same. Okay? And in fact, the only way to say that the means of two populations are equal is to actually compute the mean of the entire population and compute the mean of the other entire population, and then say, oh, after observing everybody in this population and everybody in this population, yes, indeed, the means are the same. That's the only way we could actually say the two means are the same. And we're just not, statistics isn't set up to do that. We can only say, we have evidence that they're different. I don't have evidence that they're different. Okay, it's 9:10. We're a little bit behind, so we'll take a small break if you guys need to use the restroom or just stretch or something, and try to keep it on the shorter side. We just want to cover a little bit from chapter 7, so.